So when last asked me whether there is any Chinese participant, I had to recommend Feng Xiao from Peking University, who recently discovered something quite unexpectedly, I guess, about symmetry breaking in microcavities. So today he's going to present us his work. And he's the only Chinese representative. Actually, there are two. Mulinke, who could not join us here for this conference. Well, this allowed by his doctors, was supposed to present also this week.
Okay. So thanks a lot for this kind of introduction. I'm Feng Xiao from Peking University in Beijing. And actually, unfortunately, I had no opportunity to meet Robert. So I cannot tell you any story about him. But anyway, as a PhD in physics, so certainly I know the spontaneous symmetry breaking, BEH mechanism. So, okay. So, but I think about 3 years ago, I didn't think I will have a chance to study or to do something related to spontaneous symmetry breaking. And also, I don't think I will have a chance to talk about something about the spontaneous symmetry in this kind of great conference. Okay, so actually, my group at the Peking University is focusing on ultra-high Q microcavity photonics and optics. So we did, yes, last year we published a paper in PIL to show experiment result of observation of spontaneous symmetry breaking in optical microcavity. So I think it is the reason I got this invitation. So thanks a lot for the organizers. So actually, I think this single work does not support me to speak 40 minutes. Okay, so today in my talk, actually, I will first spend 50 minutes to introduce some concept or applications of ultra-high Q microcavities. And then I spend about 20 minutes to introduce this work. Okay, so this is the first part. So before my talk, I would like to thank my collaborators and also the students, current student and the former student in my group. Okay, so this is part one, so ultra-high Q microcavity photonics and optics. As you know, the interaction between light and matter actually plays a central role in both fundamental optical physics and applied photonics. For example, if you want to generate quantum light, so you have to for example, to realize the interaction between a single atom and a single photon. And also, if you want to obtain functional photonic devices, in most of the time, you have to require the strongly enhanced interaction between light and matter. While you know for the typical wavelength for a photon is about 1 micron, while a typical matter as a single atom, the size should be smaller than 1 nanometer. So I think there is a very big mismatch in size between a single photon and a single atom. I think this case is very similar to the case of the elephant and the ant. So I think you can imagine that it's very difficult to build an interaction between an elephant and an ant. So yes, the interaction between we do have interaction between a single photon and a single atom, but typically this kind of interaction is very weak. So over the past few years, people began to study optical microcavities. So actually, optical microcavity provides an excellent platform to strongly enhance the interaction between light and matter. So these actually are some representative optical microcavities based on different confinement mechanisms. For example, fiber pellet microcavity, lunar oscillator supporting whispering gallium modes, photonic crystal nanocavity, plasmonic microcavities. So if you compare all these types of microcavity, actually they have their own advantages. So it's very hard to say which kind of cavity is the best. But anyway, in my group, we are more interested in this kind of microcavity supporting whispering gallium modes. So because this kind of, because they have ultra-high Q factor, very small modern volumes, and also typically they can product it on a silicon chip. Okay, this is actually a very short overview of the history of the whispering gallium mode microcavities. So actually from acoustic wave to microwave. So current interest in studying whispering gallium mode is in optical domain. So it's very easy to understand that whispering gallium mode in optical object. So if you have a low tension symmetrical microcavity, so light can be traveled in the microcavity because of the total total deflection. So you know that this kind of this kind of mode actually are traveling on the boundary of the microcavity. So this is show you how to fabricate such a high Q microcavity. I think no one here will be interested here, so I just skip this slide. So actually, this is a silicon microtoroid actually fabricated by our group. So originally, actually, this kind of cavity was introduced by Kelly Wahala at Caltech. So actually, this is a silicon toroid supported by a silicon wafer. Okay, this is a silicon pillar supporting a silica disc cavity. So the typical diameter of this kind of cavity ranges to 10 microns to several hundred microns. So even actually, even they're fabricated on a silicon wafer, the Q factor can be as high as 10 to 8. That means if a photon is coupled into the microcavity, the photon can travel within this microcavity for more than 100 nanoseconds. So actually, this is a very long time. Let me give you another example. If we couple 100 milliwatt light into the microcavity, after a very simple calculation, you can find that the intracavity power can be as high as 10 kilowatt. So if you calculate power density, it's also a very huge number. So considering this very weak input. So you know, because this kind of cavity, because at a high Q factor, very small volume, so provides excellent platform for studying the stronger interaction between light and matter. So in the following, I will show you several typical applications by using this kind of microcavities. So because this microcavity is also a cavity, so basically we can use this microcavity to generate resin. So for example, this microcavity is made of silica, so very common material. So we can generate ramen resin from this very simple structure. So the typical threshold for this silica microcavity resin is about 100 microwatt. That's quite low. So and also if you compare the conventional efficiency of this ramen resin, I think the conventional efficiency should be greater than 30 or 50%. A very recent direction by using this microcavity resin is we can generate microcomb. So basically, for example, if we inject single frequency light into the microcavity, after a cascaded four-wave mixing processing, so this is a typical nonlinear optics process. So from output, you can find a very broad, the output shows a very broadband spectrum. Actually, this is a microcomb. Is a frequency, optical frequency comb. As you know, comb is very important to bridge the high precision of optical and microwave applications. So the second example for this cavity application is to study cavity quantum electrodynamics. Basically, if we put a single atom into the microcavity, so because of the stronger enhancement, so basically we can reach the strong coupling between a single photon and a single atom. So basically, for example, to show the strong coupling, that means the coherent interaction rate strength between a single atom and a single photon is greater than the dissipation rate of the system. For example, G is greater than kappa and gamma. kappa is the decay rate of the cavity mode. Gamma is the spontaneous emission rate of the atom. Okay, so basically, if you can reach the strong coupling cavity QED, basically you can do some application. For example, quantum information. You can also generate quantum routers and some other quantum devices. Okay, so another example of the whispering Gaussian mode microcavity is to study cavity optomechanics. So as you just show you, so 100 milliwatt light, when this kind of light is coupled into microcavity, the intracavity power can be very high. So this very high intensity light is traveling into the within the microcavity. It will produce a very large optical force on the cavity body. Okay, so basically you can build an interaction between the optical cavity mode and the mechanical oscillation of the cavity body. So basically, in a very important themes in cavity optomechanics, basically we can, for example, we can cool the mechanical oscillator to its quantum ground state. I think it's very similar mechanism of the laser cooling process. So basically, if the input is relatively tuned with the cavity resonance, I mean the input light is relatively tuned with the cavity resonance, basically the incident photon can absorb a phonon and emits anti-Stokes the photon. So basically, this is a kind of cooling. Another case is basically we can amplify the mechanical oscillation if the input is detuned with the cavity resonance. Okay, so anyway, basically, if, for example, because the mechanical oscillator is kind of microscopic structure object, so basically we can prepare some quantum ground state and to study fundamental physics. For example, we can study microscopic superposition and entanglement in a very large scale, and we also study something phenomenal at quantum classical boundary, because it's a kind of microscopic quantum state, so can be used to do some precision measurement. For example, LIGO actually is a kind of very massive optical mechanical system. And also, because mechanical oscillator can interact with different quantum qubits, so cavity optomechanics actually provides a very good interface to do some quantum processing studies. Okay, the final example I want to show you is by using ultrahigh microcavity. Basically, we can study, for example, to highly sensitive sensors. For example, basically we can, by using this microcavity, we can realize the single nanoparticle detection or even single molecule detection. So far, so as you just mentioned, so because of a strongly enhanced light matter interaction within the microcavities, so this cavity can be used for studying fundamental physics and the photonic devices. Okay, let's move. The second part of my talk, spontaneous symmetry breaking. So in optical microcavity system. Okay, as you know, the symmetry breaking has two kinds of case. The first is the explicit symmetry breaking. So this case describes that the system itself is asymmetric. And the second one is the spontaneous symmetry breaking. So because as you know, in this case, okay, spontaneous symmetry breaking actually is very important in many areas. I just copy some words from the slides. Okay, so what I want to emphasize here is high Q whispering Gaussian mode microcavity actually is a very exciting platform to study spontaneous symmetry breaking or symmetry breaking something else. Okay, as you know, for conventional whispering Gaussian mode microcavity, it has a low tension, or it is low tension symmetric. Okay, so ideally, so this kind of microcavity always supports pairs degenerate propagating wave modes. So for example, one is the clockwise mode, another is the counterclockwise mode. So this pair of cavity modes, actually, they are degenerate. They have the same resonant frequency, same polarization, same mode field distribution, okay, but they have the counter-propagating directions. Okay, but in actual case, because of, for example, surface roughness scattering or something, for example, if a single particle on the microcavities, because of this cavity can greatly enhance the interaction between light and matter, it also enhances greatly the backscattering of even a single nanoparticle in the microcavity. So basically, because of enhanced backscattering, so basically we can build two standing wave modes. So okay, so because of the the backscattering of, for example, of the surface roughness or single nanoparticle, so a clockwise mode and a counterclockwise mode could couple to each other and form two new modes. So this is the two new standing wave modes. For these two new standing wave modes, actually, they have the balanced CW and the CW intensities. So, for example, because these two standing wave modes, one is the symmetric mode, another is the anti-symmetric mode. Okay, so in this slide, I want to show you when the symmetry breaking occurs in the microcavity. So basically, the intensities of the CW and the CW waves, so are no longer balanced, and you can basically generate the chiral optical fields within the microcavity. So for the chiral optical fields, so the intensities of the CW and the CW waves are different. And actually, in optical microcavity photonics, so actually chiral cavity field actually is very important for many applications. For example, basically you can generate unidirectional micro laser even for particle detection and for optical gyroscopy. Okay, so previously, most people, actually most groups in the world actually study the explicit symmetry breaking in optical microcavity. For example, by using wave effect, to generate local clarity, by using periodic time reversal symmetry breaking to generate overall or whole clarity. Okay, so in this case, for some wave effects such as GH shift, French shift lift filtering, and for the next case is to generate over clarity. So for example, you can design the shape of the microcavity. You can also introduce the asymmetric scattering within the microcavity. You can also, for example, rotate the microcavity. In that case, basically you can generate chiral optical fields in the microcavity. So this actually some slides show you how to generate the chiral field. So anyway, by using the explicit symmetry breaking. Okay, I just skip these slides. Okay, for example, by design the microcavity shape, so it's kind of spiral microcavity. So this any limison and many kinds of microcavity with different shapes. And you can also, for example, to introduce asymmetrical scattering. In this case, for example, if you introduce two nanoparticles or two scatterers on the microcavity, on the boundary of a microcavity, that is within the microcavity modes. So basically, because of these two particles has a different size, different scattering strength, because of the interference effect. So basically, you can generate asymmetric scattering. So then you can generate the chiral optical fields within the microcavity. So previously, it is a standing wave mode with the balanced CW and the CW components. But in the presence of the asymmetric scattering, so the field become highly chiral. So you see, for example, either CCW is dominant or CW is dominant. Okay, anyway. So by using this is actually is a theoretical prediction. So this 2 years ago, people has already realized this phenomena. So in the experiment, so in experiment, just they use a 2 nanotip to simulate 2 nanoparticle. So basically, they generate the chiral field. They also recently, last year actually, in the Nature paper, they also used this kind of this chiral symmetry at the excitation point to greatly enhance the sensitivity of detection single nanoparticle. So anyway, I just mentioned if you rotate the microcavity, basically you can also, because of the secondary effect, you can also generate the chiral field. Okay, also actually spontaneous symmetry breaking also actually attracts much attention. So in optical domain system, so but however, it's elusive experimentally, and because they have to demand multiple identical subsystems. For example, two waveguides, 2 molecules, 2 nanocavities. They should be identical. Okay. So in this talk, so I want to show you an experiment in our group. So we observed spontaneous symmetry breaking in a single microcavity. Actually, this work was not designed by our group. Actually in our group, actually we first observed the experimental phenomena. Then we found the explanation by using spontaneous symmetry breaking. Okay, so in our device, actually we have a single microcavity. So this cavity is made of silica. So it has the nonlinear effect in the microcavity, nonlinear optical effect in the microcavity. So basically, because of the intrinsic coupling, for example, a single nanoparticle or surface roughness. Okay, so basically we can build 2 standing wave mode in the microcavity. One is the symmetric mode, and another one is the anti-symmetric mode. Okay, so for these 2 standing wave modes, they have like equal CW and CCW components, but have a different phase. Okay, then we introduce the curl nonunity into microcavity. Actually, we don't need it to introduce because of the material. So if there is a light into in the microcavity traveling, so basically we have a curl effect in the cavity modes. Okay, so basically we have the surface modulation and the clock phase modulation. So because curl nonunity includes these 2 kinds of effects. So basically we can write the equation of motion to describe this very simple device. So this is originally. So now this is, because of the curl nonunity. So this curl nonunity introduced 2 effects. The first one is to introduce mode shift. So this mode shift, and also the curl effect modulate the coupling between the clockwise mode and a clockwise wave and the counterclockwise wave. So basically, you can achieve an effective coupling between the CW and the CCW waves. Okay, so basically, in a symmetrical and anti-symmetrical modes, the CW and the CCW components actually are in phase or out of phase. So basically, the effective coupling actually are totally different for symmetrical mode and anti-symmetrical mode. Okay, so basically, you see, we can study the mode property in the Brout sphere parameters. So basically, we can write the CW component and the CCW component in the two parameters. One is the theta, one is the phi. Okay. So basically, for the symmetric mode or for anti-symmetric mode, so this is the phase space. So actually, this is described the asymmetric mode because phi is equal to pi. And here, why this red point actually describes the symmetrical mode. Then, if we increase the intracavity power, so the current nonlinear effect is stronger and stronger. So you can see without nonlinearity, nonlinearity is higher, higher, and higher. So above threshold intracavity power, and this threshold corresponds to the intracavity power, you can find that the asymmetric mode, okay, becomes unstable and form two new modes. So these two new modes actually, first one is a clockwise Kähler mode, and other one is the counterclockwise mode. So this is because theta is greater than pi over 2 or smaller than pi over 2. So you can see here. So basically, we can also so actually this is we said is the symmetry breaking of the cavity mode field. You can also study this kind of symmetry breaking by plotting the potential well governed by the equation just mentioned. Okay, so when the nonlinearity, optical nonlinearity is very weak, so it shows here. So this is when the power, intracavity power is at a critical point, so come here. When the nonlinearity is very strong, so you show here. Okay, you can also study the simulate the optical fields in the microcavity by adding the nonlinearities. So without nonlinearity, so the mode pattern shows very clear standing wave mode. Okay, while if we introduce the nonlinear coupling, so you know the mode becomes not so clear. It's because it shows some behaviors of the propagating problem in nature. So far we have introduced the idea to study spontaneous symmetry breaking in optical fields. So in an experiment, so we first fabricate a high Q microcavity with Q factor is greater than 10⁷. And this cavity actually we also to change the intracavity power. So basically we use a variable optical antenna to control input power precisely. So this is a top view of our microcavity. So we use the bus fiber to excite the whispering gallium modes in the microcavity. And also we use the second fiber, that is a drop fiber, to connect the emission from CW output and for CW output. Basically, by using the drop fiber, basically we can connect the CW and the CW components separately. Okay, so this is actually the experiment result. So when the excitation is from only single direction, okay, so we can record by using a drop fiber taper to record the CW and the CW output intensities. Okay, so when the intracavity power is very weak, so you can see the output power of CW and CW actually they are almost identical. Okay, so that means the intracavity within the microcavity, so it supports the standing wave modes. So actually in this case we excite the anti-symmetrical mode. Okay. So when you increase the excitation power, so you can find that there is some slight actually asymmetry between the CW output and the CW output. So when when excitation power is strong, is very strong, you can observe evident chirality of the intracavity power. And okay, and also we found that because there is a threshold, actually in our experiment you can see there is obviously threshold to observe the chirality of to observe the spontaneous symmetry breaking. Okay, so below this threshold you can never see the Kähler field And also only above this threshold, you can observe the chiral field or spontaneous symmetry breaking. Okay, so also this chiral threshold is dependent on the coupling strength. I think it's not very important, so just skip it. So in our experiment, so actually we also do a further experiment, actually, measurement. So in this case, we excite the cavity mode, so in bidirectional. So basically, that means that both the cavity or interaction has a symmetry, a chiral symmetry, and the input also has a chiral symmetry. So in this case, we can also observe the output from the drop fiber, because from drop fiber, we can separate the CW output and the CCW output. Okay, so the experiment result is here. So when the input power is weak, you see the intensities of the clockwise mode and the counterclockwise mode, actually, they are almost the same. That shows the intracavity supports a steady wave mode with the equal CW and the CCW components. Then we increase the input power, for example, to about 300 microwatt. So you see the imbalance between the CW output and the CCW output. Okay, so basically if you plot the log PCW, and the PCW is output, is the intensity of the CW output, and the PCCW is the intensity of the CCW output. Okay, if we plot log here over the input, depending on the input power, so basically you can see the obviously bifurcation behavior. Okay, so it shows a threshold behavior here. Actually, we also count the emergency frequencies of the CW chiral field, or CCW chiral field, actually. So it shows here. So almost you can see, actually we perform 31 measurements. So 37 results we observe the CW chiral fields, and 34 we observe like CCW chiral fields. So it shows almost the spontaneous symmetry, spontaneous this process. Okay, actually we are also interested to see similar work by Highest group in UK. Actually, this is another measurement. So previously we excite the asymmetrical mode, okay, but we excite the anti-symmetrical mode. So in the next experiment, actually we excite the symmetrical mode. So as expected, so when we excite the symmetrical mode, we cannot observe the symmetry breaking behavior in our experiment. So actually this is as expected, because for symmetrical mode, so the effect, the curl effect modulated effective coupling strength between CW and the CCW wave is like here. While for the anti-symmetric mode, this is minus. For symmetrical mode, it's plus. So in this case, you can never observe the symmetry breaking. So this is the last slide. Yeah, so actually, for my talk, almost the last slide. So this is a recent experiment. So in this case, in this experiment, actually, if we increase the intracavity power again, actually, basically, we can observe the lamination. What interesting thing is, even for the lamination, we also observe the spontaneous symmetry breaking. Actually, this is chirality, but depending on the laminal power. You can see, previously, people have thought because of low tensile symmetry, if you generate laminator into the microcavity, basically you can observe both CW output and CCW output. But we found that in our experiment, when the laminal power is strong enough, we found that the microcavity laminator field in the microcavity becomes highly chiral. So you see here. So this is a summary of my talk. Actually, we propose and demonstrate the current nonlinearity-induced spontaneous symmetry breaking, which emerges about an input threshold of only a few hundred microwatt. So by direction inputs, the initial standing wave mode is broken spontaneously and turns into clockwise or counterclockwise chiral states with the counter-propagating output ratio exceeding 20. And also, in our experiment, we observe the spontaneous symmetry broken microcavity laminator. Okay, thank you very much.
Right, any questions? So this chirality, oh, sorry, Matt.
Yes, in your last view graph, this point where you get the symmetry breaking, is that dependent on how quick you ramp the power?
No.
Would it occur at different?
Yes, basically in our experiment, actually, we sweep actually we change the power, input power. But in our experiment, we change the sweeping speed. It doesn't, I think the sweep does not play, yeah, doesn't matter. Yeah.
Yes, John.
Did I understand correctly? Is this on?
Yeah.
Yeah. Did I understand correctly from the first half of your talk that you also realized PT symmetric systems?
No, PT symmetric. So we didn't study PT symmetrical system.
You didn't?
We didn't, yeah.
Is it interesting?
So basically to study
It's
PT
not
symmetrical,
on the
basically okay, I see. Basically you have to use a coupled microcavity. For example, one microcavity has a loss, another cavity has a gain. So basically coupled together, you can basically observe the PT symmetry broken.
Right.
But in our case, we use a single microcavity. So I don't know how to, for example, to realize or observe the PT symmetry breaking in our system.
In principle, you can imagine that such devices can be used as a gyroscope.
Okay.
But how sensitive would it be
How sensitive for
to detect the rotation of the device? If you
sensitive to
the Earth rotates, but also if you just rotate the device,
you mean rotate
the
the
two directions should have a different relative speed, so that you detect actually in inertia you detect the rotation of the whole device.
detect rotation?
Rotation.
What?
If the device rotates,
Rotate. Okay.
then the wave should be going in the same way. Which
Okay.
means
So
that
I think
in
you mean
principle,
the experiment by another group, right? You mean here?
yeah, I'm not sure which picture should be most appropriate, but if you have this circular resonator,
Yes.
and you have two waves going into
Yes,
it
yes.
simultaneously,
Yes.
then if you rotate the device,
Yes.
the waves themselves should not rotate or rotate differently.
They're not detect. I think the degenerate is lift actually by rotating the microcavity.
So would the waves follow the rotation, or would you in principle be able to detect the rotation this way,
Detect rotation.
to observe?
Yeah, can you measure the split?
Yes, basically we can match. So basically, for example, in this paper, they use this kind of the splitting actually, or split, to measure the rotation speed.
Yes.
So this,
So the question is really, how sensitive would that be?
I don't know. Sorry.
Because it's,
Sorry.
it's microscopic, so in principle you expect it not to be very sensitive.
I don't. Typically, for this kind of this phenomena, I think the sensitivity is proportional to the area actually for the microcavity. I don't think the sensitivity will be very, very high. I don't think so.
So the area is too small,
Yeah.
of course.
Yeah.
Yes,
Yeah.
thank you.
Yeah.
Right. If not,
Maybe,
yes. Sorry, John.
I think you did mention that these cavities might have applications for particle detection.
Yes, yes.
Could you describe the basis for that?
Okay, so basically, conventionally, when a single particle is entered into the microcavity, so the particle will induce several effects on the cavity mode. For example, mode shift, mode splitting, or mode broadening. This is a general detection mechanism for microcavity sensor. So by using, for example, by using here, so actually, by using the symmetrical symmetry breaking in the microcavity, basically we can implement, we can control the whole system, for example, to an extraction point. So along the extraction point, the sensitivity actually to a singularity particle bonding event will be greatly enhanced. So actually, this is an experiment by Nanyang group at Washington University in St. Louis. So.
Is that okay?
You're thinking.
I understand the idea. Practicalities, I don't know.
Yes, yes.
Okay.
That needs more experiment, I guess.
Okay.
Yeah. Right, thank you.
Thank you very much.